Hello everybody, I thought I'd do a quick video on how to thread mill holes to suit HeliCoils. So I have a part here. I can't show you the whole part, but I can zoom in on this particular feature. So I've got a bore here with 8 holes around it. If I look at the GD and T drawing, it tells me that I need to drill and tap these holes to suit a wire thread insert. And these wire thread inserts are for an M5 by 0.8mm pitch screw. So a 0.8mm is a coarse pitch. For an M5, I think a fine pitch would be 0.5mm. 6H tolerance, which is a fairly loose standard tolerance, and then that's just a British standard call out. So that's what I need to do. So I think first of all, I'll probably do a quick explanation as to what a HeliCoil is, why you would use a HeliCoil, then why I would go about thread milling holes rather than using a tap, and then of course I'll get into how to actually program it. So where you get the data from that you need to put into Fusion 360, where you actually input that data in Fusion 360, and then a few things to watch out for as well. So if I bring up this picture, this is actually what a HeliCoil looks like before you insert it. It looks a bit like a spring. It's not very springy, but it looks a bit like one. You have a tool that engages with this little prong at the bottom here, and you'll notice it's almost snipped off there. And what that allows you to do is to screw it into a threaded hole, and then once it's in, you get a punch, and you hammer that punch, and it knocks this bottom bit off, which allows a screw then to go right the way through the helicoil. So it'll look like this once it's in the hole. Well, that's it, without being cut in half, but that is obviously it cut in half so we can see how it works. Why would you use these? So you typically use them in softer materials like plastic, aluminium, composites, etc. And these helicoils are, well, I've only ever seen them in steel, but they're essentially made from a harder material. And it means you can screw a screw in and out over and over and over again without worrying about wearing out the thread, or if you accidentally over torque it, you're less likely to strip the thread. So that's the principle behind them, and hence why you see them in softer materials. You'll see the pitch call out for a helicoil. Something to note while I've got this drawing up is that the pitch on a screw, say for instance our M5 coarse pitch is 0.8mm, is the distance between that point and this point. So for one full turn around the circumference of the hole, whatever size that hole is, the pitch is telling you how far it will drop down. So 0.8mm in our case. So you'll see that the pitch on the inside of these helicoils is the same as the pitch on the hole that takes the helicoil, and obviously the hole that takes the helicoil has to be oversized. So we'll get into that information later, but I'm just pointing out while we've got this picture up that the pitch stays the same for a normal threaded hole. So a normal M5 threaded hole, it's 0.8mm, and then for a helicoil hole it also stays at 0.8mm. It's probably useful also to point out that you measure a helicoil hole, that 6H tolerance that is on the call out, so that tolerance call out there, you measure it in the same way as you would a normal threaded hole. So you use a go no-go gauge typically. You'll see these helicoil holes often referred to STIs, so that is short for that, to suit wire thread insert. So I think it stands for standard wire thread insert, something like that. But you'll see it called an STI, or in this case an EG. So if you're searching for a go-no gauge, search for STI, which stands for something a bit different where I'm from, but anyway. So the principle behind a no-go gauge, if you've not seen it, is if the hole is undersized, this go side won't go in. If it's large enough for the go gauge to go in, that means the hole is not undersized. But then if the no-go side, this bit with the red on it, can go in, that means it's oversized. So you want this side to go in, the go side, but then the no-go side to not go in, and that means it's within the tolerance range. And again, coming back to CAD here, what I'll show you later on is what I'm doing here, because there's actually a degree of, one of the advantages of thread mills is they allow you to adjust the size of the holes while still being in tolerance, whereas a tap, you will just get one size of tap basically. You don't, which will obviously keep it in tolerance, but you can't slightly adjust it to make a tighter or looser fit. So that's one of the things I'm doing here, which actually brings me on to the benefits of thread milling versus tapping. So that's one of them, that you can adjust the fit of a hole while still keeping it within the tolerance range. That's why I'm doing this. I'm doing this for my clients. So they've asked for basically as tight a hole as they can get while still being easy to insert the HeliCoils. So I'm basically giving them a range of options here. These numbers are offsets, which again I'll show you in the calculation what these are, or how we get these numbers in a bit. But I'm showing them the different offsets, and they can basically put HeliCoils in these holes and say, okay, that one's a bit loose or that one's a bit tight, and they'll find one that works for them. And it means I'm not on the hook as well, for, you know, it's up to them to decide. I'm not on the hook, so I don't make a part and then they reject it. So the other advantage of thread milling, so obviously you've got that. Thread mills, if they break in a hole, because they're using this whirling effect, so you go down into the bottom of a hole, we're climb cutting, so it whirls upwise, so it's cutting clockwise basically, so that's why it has to go to the bottom of the hole and whirl its way up. If that tool were to break, you're unlikely to scrap the part. You can basically just pull the broken thread mill out and then go in with another thread mill, and it's likely that threaded hole will be fine to use. Whereas if you're using a tap, the tap is very hard. If a tap breaks, it's basically impossible to remove without scrapping the part. You probably have to drill it out and then do an oversized hole and then tap it to take a larger screw than you originally intended. That's probably the only way you could save a part. Thread mills are very versatile. That's another benefit. So you can get, if I bring up the catalog, so you see here I've got a single point. You can get multi-point thread mills, but I've got a single point thread mill. So here's an M5, it's by 0.8mm coarse thread end mill, and that will do through holes, blind holes, all sorts of threaded holes. You're not having to, whereas taps, you might have different sorts of taps for blind holes and for through holes, etc. So yeah, versatility is great, and they're also versatile in that you can use them in a standard collar, whereas with a tap, you typically buy a tapping collet, which you may not have on the shelf, or you may, you know, you're only ever, say I was doing a strange hole size like an M5.5, going to the expense of buying a collet for it seems a bit silly, especially if you're just doing like a one-off part or something. So that's why a lot of people are reluctant to use taps and so on, especially for one-off parts. Whereas this M5 here, for instance, you just buy one, it'll do almost everything you need at any point in time. Maybe not as quick as tapping in certain instances, but the flexibility is often what you're looking for. You don't have to worry about chip evacuation with thread mills because, again, they're undersized for a hole, so you can get lots of coolant in there and wash the chips out and so on and so forth. So there's a number of advantages, and you'll actually find in harder materials like titanium that you just won't find taps because of the forces involved. You nearly always have to thread mill, whether it's an internal thread or an external thread, because obviously thread mills, because they work like an end mill, they're just taking a lot lighter cuts, so therefore there's less cutting forces involved. So how do you go about programming a thread mill, a thread milling cycle? So I'm in Fusion 360 here, but I'm sure these principles apply to anyone else. So if I, or any other CAD/CAM software, sorry. So if I click edit on this thread mill cycle, take a little while to load, but what it's going to ask me for is really three key pieces of information, or four. So the first of all is obviously the thread mill that I'm going to use. That has to match the size of the hole, so that's the first bit. The second bit is the hole, and I'll get into this later on, but it's very important that the hole you have that is actually modelled reflects what you use in your calculation. So I'll show you that in a little bit. So that's first key piece of information. Then you've got the pitch, which is fairly standard. You just really have to watch whether that's coarse or fine there, whether you're doing a coarse or fine pitch. and then the pitch diameter offset. So this is the main thing that causes people issues. So I'll close that and I'll open up this Excel spreadsheet, and I'm not sure if I've got it open, but here we go. So this is from John Saunders of Saunders Machine Works, his YouTube channel. I'm sure a lot of people have seen NYCNC, but if you go on his website, you can download this. It's a really good resource, and the idea is that it basically allows you to get your threads right first time. And the reason for that is that it's accounting for the tip of a thread mill. And I don't want to go over what he's already done, so I'd say before you watch this, go and watch this video about how he's doing the calculation, how this spreadsheet works, and then come and watch this video for HeliCoils. So I'm starting off with a standard M5 thread here, and then we'll get into the HeliCoil sheets here. So I'll start with the standard M5 and how I'm putting the data in, and then I'll talk about how that changes for a HeliCoil M5. So what I'm doing is I'm going to a chart like this. So you can see these are all over the internet, and they're charts for threadmilling. So they just give you a range of parameters here. So you go down the side, search for the thread that you're using. So there is an M5 0.8mm pitch, 6H tolerance. And what it does is it gives you the drill size, so tap drill. So for us it's 4.2. I've lost it. There we go, 4.2. And then it gives you a range between the minor diameter and the major diameter. So what is the minor diameter? What's the major diameter? The minor diameter is basically the inner hole. So typically you would drill that, but maybe for a larger threaded hole, you would interpolate that with an end mill. And handily, it gives you a range. So I've lost it again. There we go. So it gives you a range 4.134 to 4.334, but it actually tells you the drill to use. So it's saying use a 4.2mm drill here. Then it's giving you the major diameter, and the major diameter is basically where the thread mill goes out to. So I've kind of modeled it in our example here for a helicoil, and that is, if you can imagine, the point on the thread mill wants to come in contact with the outside of this hole. So that offset number that we saw in this parameter here, it is basically telling you the distance that it needs to go from this hole to get to this line here, this hole, this imaginary major diameter. So that's so whatever this inner hole is, you have to get that right, because if that's 4, it's going to need to be more to get out to this line. So that's really why it's so important to understand the size of this inner hole. So for an M5, we're going with 4.2 millimeters. Oh, I've actually put it in as 4.3. I don't know why I've done that, but we can change that. 4.2, 4.2. So what's happening here is I'm working in metric. John Saunders is in America. I'm in the UK. John Saunders is in America, so he's working in the imperial system. So what I'm doing here is getting the metric numbers, then I'm converting them to inch. So that's what this 25.4 is here. So I get this measurement, and then for this box here, I'm basically saying take that number and divide it by 25.4. And then this is inserted into the spreadsheet. So you've got the major diameter here. He set it up so you have a minimum minor diameter and a maximum, but if you're drilling, they're both the same. You don't need a range, so I think he's actually overcomplicating it here. Then the beauty of this spreadsheet is it accounts for the size of the flat on the end mill, so the thread mill, sorry. So what do we mean by that? They give you a cutter diameter. John Saunders explains this in his YouTube video. So again, watch this. So I'm not going to go into too much detail, but basically you need this diameter, and then you also need the length of the flat. So here it tells me 0.125 times the pitch. So our pitch again is 0.8 millimeters. So you'll see I do a calculation here. 0.8 times 0.125 gives us 0.1. That feeds into here, 0.1, converts it into inch, and then feeds in down here. So this, you're basically just inputting the numbers that you'll typically get in your catalog and then off the chart. So the tooling catalog, one like this. This is for ITC, good UK tooling brand. And then you'll get it off your chart as well. So again, these charts are all over the internet. You won't have trouble finding them. So you're inputting that data, and then what it's doing is spitting out a pitch diameter offset for you, and it's giving you a choice of either the minor or the major, and that has to do with whether you model your hole to the minor or major diameter. So if I had modeled the hole to basically be this extruded down, that would be modeled to the major diameter, so the offset will be very, very small. So yeah, tiny, 0.01 millimeters. Again, I'm giving me an inch, so I'm just doing conversion to metric here because I'm working in metric. So you'd get a very, very small offset, whereas because we have our hole here modeled to the minor diameter, it's basically saying, okay, we're going from this hole and we're stepping out. We would be stepping out if we were doing a normal M5 hole, 0.93 millimeters. So going from there to there is 0.93 millimeters, and that will give you mean the outside of that thread mill is getting as close as possible to this line, which means it will almost perfectly be in tolerance. So it gets a little bit more complex with HeliCoils because the information is harder to come by, and this is why I'm doing this video, really, because I struggled to find this information. But after searching on a few forums, I found this chart, so stanleyengineeringfastening.com, and I'll link to this below the video, but you can see it gives me parameters for that larger oversized hole to take the helicoil, and it's actually telling me that the minor diameter here for aluminium is different to steel, and so on. So we're going to have a 5.2 because we're doing an aluminium. We're going to have a 5.2 millimeter inner diameter, and then the complexity. So this is the drill specs. That's inch. Where's metric? Here we go. So M5. So it only gives me the maximum. It doesn't give me a range for the tap major diameter. It only gives me the maximum. So I'm going to take these numbers. So the maximum is 6.145. So I've put that in here, 6.145, and then converts it into inch, and that feeds through to here. The size of the flat that's going in down, so convert equals 0.1, gets converted here, feeds in over there, is the same. We're using that 5.2, so that feeds into these numbers. So it takes all those numbers and spits me out these two imperial measurements, which again I convert into metric. So you can see here I have 0.96, and then these numbers start to make a bit more sense because I've got 0.94 here, and I'm basically working down. So I know that 0.94 is going to be within tolerance. If 0.96 is my maximum, if you remember, we're working with the maximum 6.145. So this number here, this offset number, is the maximum we can have. So I'm working down from that in here. So my customer, my client, is going to get this, and they can test. And I know that 0.94 is pretty much the maximum I can have while safely being within tolerance for the offset number. And then I'm working down in size, and they can decide how tight they want it, basically. So if I go to edit, you can see I've got 0.82, 0.82. So there's not a huge amount more than just doing a standard thread milled hole. There's just these things to know, where to get the information, and that you'll probably have to work down from that maximum tolerance and find a correct fit because you're only given that maximum size. Probably something to note as well, that's really important to note, is that if you look here, I have this hole modeled to 5.2. So it matches what is in my calculation, 5.2. That's really important that what you have modeled matches how you're doing the calculation. So for instance, on the actual part, you'll see that these measure 4.134, so 4.134 diameter, which sounds like an odd number, But if we go back to our charts, if I can find it, which one was it? That one. So that is the minor diameter for an M5. So the minimum size for the minor diameter of an M5 thread. So if I'd just gone in on this hole and said, oh, I'm going to go in with a 5.2 drill, but not accounted for the fact that the hole I'm modeling off is the wrong size, then my calculations would have come out wrong, because Fusion isn't smart enough to recognize when this hole is undersized. It's just, this hole could be 10 millimeters, it could be 3 millimeters, and it's just offsetting from that hole outwards to this kind of imaginary line, however much you tell it to. That's all it's doing. So your hole here must match whatever you've got in your calculation. So that's really important to know. And I don't think there's, from the videos I've watched, I don't think they make enough that point very well. So yeah, you can actually have that whole model to whatever size you want, but just make sure it's matched in your calculation. So I could say, for instance, I didn't want to mess with my model here. You know, I didn't want to tamper it, or even if I wasn't allowed to by the customer, I had to, you know, not tweak it at all. And I had to use that measurement of 4.134. Then I would still obviously go in when machining with a 5.2 millimeter drill, but I could change this measurement to 4.134. Ignore this wrong tool thing, and it would give me a different offset. So yeah, you still drill with a 5.2 millimeter, so ignore this wrong tool thing, because that basically thinks there's going to be a collision between the neck and the, because it thinks the hole is too small for how far you're offsetting. So it's quite, again, another good feature of this spreadsheet, but we're obviously going in with a 5.2 millimeter drill, so we're going to have more clearances than this thinks we have. But it's telling you, if you do your calculation from that, you're going to need to offset it by more. So just bear that in mind. Otherwise, HeliCoils are very similar to standard thread milled holes. If you've got any questions, just comment below the video and let me know. I will also be doing more videos like this with tips and tricks. So if you found this one useful, hit the subscribe button and it will notify you when I release a new video. Alright, thank you very much and bye for now.